Welcome dear students, we are discussing the flexible electronic devices, or we can say flexible energy storage devices. So in this lecture we are discussing the various flexible supercapacitors, how we prepare them, how we use them. So in this series we just take the another supercapacitor, and supercapacitor use the electrodes, and we are discussing the various electrodes. So electrodes must be flexible and must be compatible with this another devices. So multi-layer composite electrodes we will use. So that is the fabric electrode. That is a fabric electrodes. How we prepare these fabric electrodes? We use the screen printing and the reduction method. So there is one of the scientists who have proposed a multi-layer composite electrode made of the copper nanoparticles, reduced graphene oxide and the cotton fabric. So in a three-dimensional structure. That process involved in silk screen printing of graphene oxide onto it. So the cotton fabrics, which was then reduced to RGO using the Na2S2O4 solution. So the process is safe, effective, eco-friendly and repeatable. So copper nanoparticles were synthesized on the RGO reduced graphene oxide surface through in situ polymerization using a water bath and ultrasonication. So that polymerization using the water bath and the ultrasonication. So without the need for elaborate or expensive procedure. So it is very easy. We just through in situ process synthesis of carbon nanoparticles on the reduced graphene through the polymerization, where we use the water bath and the ultrasonication. So the utilization of the eco-friendly material made this process as environmentally safe alternative, except for hydrise. We having a hydrate. Moreover, it has been discovered that the pollution diffusion caused by the fabric electrodes can be reduced by adding graphene to them. So to achieve this, multi-layer structure was built using copper. So copper, a widely used metal known for its good electrical conductivity. So copper nanoparticles were stacked on the electrode surface to increase their storage capacity. So copper nanoparticles were stacked on the electrode surface so that we can increase the storage capacity. So this three-dimensional this three-dimensional effect in the fabric electrode resulting in a good charge discharge performance with a specific capacitance of 197.4. that is the good score for the charging discharging performance by various processes where various multi-layer structure development. So a symmetric supercapacitor made entirely of solid material was also developed, and it shows a specific capacitance of 179.4. So a maximum energy density of 8.52 and the power density approximately equal to the 100. So this fabric based electrode is an attractive option for wearable devices, as it is having a low cost and easy to produce at a large scale using commonly available material. So we are having a wearable fabric deposited supercapacitor at the low cost as well as easily produced, as well as we can prepare on in a mass scale. So metal oxide based supercapacitors have appeared as a promising option due to their high conductivity, structural tunability and redox activity. So another type of supercapacitor is the metal oxide based supercapacitors. Again, that has been taken from the one of the research paper that has been defined. Zaho, we developed the flexible bimetallic electrodes composed of ultra thin nanopetals grown on a nanoporous nickel oxide hydroxide at the rate of nickel core shell structure for the wearable electronics. So easily we can remember it that we have developed the flexible bimetallic electrodes that is composed of the ultra thin COH and nanopetals that grown on a nanoporous nickel oxide that can be the core structure for the wearable electronics. So it was fabricated via the de-alloying and electrodeposition method. So the fabricated hierarchical porous structure demonstrated enhanced ion transport, high effective surface area, high capacitance and wider voltage window compared to a single metal oxide. As we are using the multi bimetallic, so it is giving the better result as compared to the single metal oxide. So they assembled all the solid state using the hybrid electrodes, like this is that can be hybrid at the rate of nickel foil. So delivering 59.2. Moreover, these supercapacitors have superior performance after multiple bending and deformation, along with an 81.6% capacitance retention rate after 800 cycle. It is also having a long cycle. So you can see on the screen that we are having the various methods for the preparation of the wearable supercapacitor. So you can see here that here we are having a surface area where we are having a screen printing, then there is a GO fabrication, then we reduce that graphene oxide, after that this is just deposit on the layer, and then final product you can see it is in the form of the copper reduced GA oxide, like we can have the fabric type of material, and on that we can just prepare the storage device. So image illustrate a multi-step fabrication process for creating a functionalized textile, specifically a copper reduced graphene oxide cotton fabric, and that fabric we use for the preparation of energy storage devices as well as supercapacitors. So this process typically aims to develop the flexible electrodes for wearable electronics such as supercapacitors or the sensors. So what is the fabrication process breakdown here? First is the screen printing cotton to geo cotton, that is a reduced cotton. So cotton fabric is used as a base substrate, then graphene oxide is applied to the fabric using a screen printing techniques. This transform the plain cotton onto the GO cotton, which is non-conductive but coated with the graphene oxide layer. Second is the reduction of the graphene oxide, that is GO cotton to the RGO cotton. So RGO cotton is immersed in a solution for the chemical reduction. So this removes the oxygen containing the group of the GO, converting it into the reduced graphene oxide. So that is the RGO. This step is too critical because RGO is electrically conductive, whereas GO is an insulator. So, third step is the in situ polymerization. So, in polymerization we use the RGO cotton to GO-RGO cotton. Now, we are having the final product. So, the RGO cotton is placed in a beaker where a secondary material is introduced via a in situ polymerization. So, based on the final label GO-RGO cotton, this step likely involves the deposition of the copper nanoparticles or a conductive polymer complexed with copper onto the RGO coated fiber. So, in situ polymerization allows the secondary coating to grow directly on the surface of RGO cotton fabric, ensuring the better adhesion and more uniform coverage. So, the final material structure we got is the insert in the bottom left magnified via the GU-RGO cotton fiber that illustrates a three-dimensional porous texture where the individual cotton fiber are coated with a composite layer of RGO and the copper. So, creating a conductive network suitable for electronic application. Another method is the preparation of the FOPLA and the Pani FOPLA electrode, that is the two-stage synthesis process of a flexible conductive electrode material. That is the two-stage synthesis process of the flexible conductive electrode materials. So, you can see here that how they are forming. We will see step by step that how we can form the Pani FOPLA. They are the various steps. So, we discuss the steps one by one. First, this diagram illustrates the two-stage synthesis process of a flexible compatible electrode material, that is polyaniline coated formed polylactic acid, that is the PLA, PANI to FOPLA, formed in the form, that is why it is a Pani FOPLA. The first stage, what we do, just fabrication of the formed PLA, FOPLA, formed PLA. So, process begins with the non-solvent induced phase separation, that is an NIP method to create a porous structure. So, solution preparation, where we are having the polylactic acid, that is PLA, is dissolved in the dichloromethane, that is DCM. So, that is a phase separation. This solution is introduced into the ethanol. So, that is a non-solvent. So, evaporation, as the ethanol and the TCM evaporate, the PLA solidifies into a 3D porous form structure. That is why it is a FOPLA. Now, tailoring, the resulting form is cut or shaped into the desired dimensions for the electrode. The another stage is the synthesis of the PANI for FOPLA. So, the FOPLA scaffold in then functionalized with the conductive polyaniline, that is the PANI, through in situ oxidative polymerization. So, that here we are having a reaction mixture as well as polymerization. Now, the reaction mixture, the FOPLA scaffold is immersed into a solution that containing the aniline monomers, that is AN, that contain the sulfuric acid also as a dopant, and the ammonium persulfate. So, we are having a three material that are as a oxidized initiator. Another is a polymerization, that over a period of the 2 hours, aniline that monomers polymerize directly onto a porous internal and external surface of the PLA form. So final product resulting PANIFO-PLA composite combines the mechanical flexibility and the strength of PLA form with a electrical conductivity of a pani coating, so making it suitable for the application like flexible supercapacitor. So another method is the free standing electrode composed of antimony few layer SB, carbon nanotubes and the polyaniline, that is pani. So development process of a SB oblique CNT oblique pani composite film electrode, that is also a multi-layer film. You can see here in the diagram, this is the very simple process that you can have how we prepare that type of fabric or the flexible substrate. First, here we are preparing the electrodes for the electronic devices. So, fabrication process for a flexible freestanding electrode composed of antimony few layer, we can have the few layer of the SB, that is the another is the carbon nanoparticles, and that here we are using the polyaniline, that is pani, similarly as we have taken the previous. Now here we also have the polyaniline. So this specific composites is typically designed for the high performance flexible supercapacitor. So we are having the step by step how we do it. First, exfoliation of the antimony. So bulk SB to few layer, we can take, first we take the bulk, then we take the few layer from this. So the Prof sonication and the solvothermal reduction can be done. These high energy techniques break down for the bulk material into the few layer nano sheets through the liquid phase exfoliation, and ice bath is used to control the temperature during the sonication. So first is a step by step breakthrough of the exfoliation of the SB. So another is the formation of the CNT framework. So CNT solution plus SB, that is the few layer antimony is mixed with a CNT solution. So we can we use the NMP as a solvent. So again after that, in this formation of CNT framework, vacuum filtration has been done. So this mixture is passed through the filter. So the result is a flexible freestanding deposition on the material, and that is as the black flexible sheet being held by the tweezers. So the CNT acts as a conductive and structural backbone for the SB sheet. So another is the introduction of the polyaniline. Now we are having the two layer. Now again just there we will there the electrode deposition can be done. So the antimony CNT film is used as a working electrode in an electrochemical cell. Now the PANI polyaniline is then grown onto the surface of the combination that we are having network via electrode deposition. The film we have prepared earlier SBCNT, now it will be used for the deposition of the PANI. So final composite, we have the result of the SB oblique CNT oblique PANI PANI composite film, that is having the green shaded film in the diagram. So we can see that that is green shaded film, that is representing the SB oblique CNT oblique PANI, and that is used for the flexible electronic energy storage devices that may be used in the sensors, flexible sensors, as well as in the energy storage devices. So another is the MOF based supercapacitor. So that illustrates the preparation process of ZnCOMOF-CS composite electrodes. So how we will do it? This is the basic diagram where we are having the ZnCUMOF. So the last product you can easily see, that is the photograph of the ZnCOMOF sheet that is used for the. So what is the process here? What we will do and how we will prepare this sheet? First we start with the GO graphene sheet. After that it will be converting into the ZnCO and MOF and GS. So what is the synthesis process for this ZnCO MOF? That is zinc cobalt metal organic framework, and GO, that is a graphene oxide, are combined. So both we will use. So ultrasonic treatment is applied for 1 hour to create the uniform ZnCOMOF and the GO dispersion. Another is the hydrogel aerogel formation. So SDS, that is the sodium didecyl sulfate, that we will use for as a ascorbic acid that is added to the dispersion. This mixture undergoes a multi-stage thermal treatment like 75 degree for the 1 hour, minus 18 degree for the 5 hours, likely the freeze casting and the stabilizing step, moreover 90 degree centigrade for the 5 hour. So there are the various thermal treatment done for preparation of the hydrogel aerogel formation. So this result in a ZnCO MOF GOS, that is graphene oxide sponge, or that is the sponge type of the structure. First we have the fabric, we have the form, now we have a sponge type of the structure. So after that the third process is the reduction phase, where the composite is treated at 350 degree centigrade for the 1 hour for the reduction. So this process converts the graphene oxide onto the graphene sheet or the reduced graphene oxide RGO, that must be the two dimensional, resulting in the final ZnCOMOF-GS product, that is we have seen in the previous diagram. So finally we are having this type of ZnCOMOF-GS, that is in the form of the fabric, and that will be used for the development of the supercapacitor. So this product is of the sponge type of material. Next is a presentation of the chemical bath deposition based synthesis process of NiCOS and CC. How we will do it? You can see that is a net type of structure. There is a more porosity, as we see on the screen, that there is a various mesh type of structure. So how we take it? So the image that we have seen illustrates a 3-step synthetic process for the fabrication a hierarchical nanostructure on a mesh substrate. So commonly we take the carbon cloth or the nickel foam. So commonly used for the high performance energy storage devices like supercapacitors. So here we are having a various method. First is the synthetic steps, that is the in situ growth. So initial substrate, that is a black mesh that we have seen in the diagram, undergoes a hydrothermal or the solvothermal reaction, where a precursor nanostructure is grown. First we are having the mesh type of structure on which the hydrothermal through and solvothermal reactions, a precursor nanostructure is grown directly on the fiber. This is often a metal organic framework, that is MOF, like ZIF 67 or a layered double hydroxide. Another is a ion exchange. So the precursor nanostructure purple and immersed in a solution where the specific ion replaced or intermixed with the original metal ions, often resulting in the charge in composition and the color. So this step is used to create the bimetallic or the multi-metallic compound. Another is the sulfidation. So the final chemical transformation involves converting the metal precursor into the metal sulfides. So using a sulfur source like thioacetamide, that is TMMA, or the solid sulfide. Sulfide are preferred for the electrode because they typically offer better electrical conductivity and high electrochemical activity than their oxide and hydroxides counterparts. So advanced electrolytes, the flow of electric currents and the storage of electrical energy are made possible by electrolytes, which help ion move between the electrodes. So electrolytes aid in the creation of the double layer as a electrode electrolyte interface in EDLC. So here the choice of electrolyte is critical for achieving the desired electrochemical stability window, so which determines the operating voltage range of the supercapacitor. So physical separating positive and negative charges, this double layer retain electrical charges compared to the conventional EDLC. Pseudo capacitors have a higher energy density because the electrolytes take part in reversible redox reaction at a electrode surface. So high ionic conductivity, low electrical conductivity, wide electrochemical stability window, chemical and electrochemical stability, low viscosity, thermal stability, inflammability and compatibility with the electrode materials are the some important requirements for a high performing electrolyte. Electrolytes are mainly classified into the liquid, solid state and quasi-solid state. So up to now we have discussed the various electrodes. So in next lecture we discuss the electrolytes for the flexible electronics energy storage devices. Thank you very much.